What is up, everybody? Welcome back to Stewart Science. I'm Mr. Stewart, and today we're talking about motion in one dimension. And so we've been talking about a few different ways that we can represent how something moves. We've mentioned that you can draw pictures of it, you can use words to describe if it's moving fast or slow, towards or away, and everything has to be compared to the observer, which is usually us. I want to start getting a little bit more technical about how we can describe this. And so we're going to use a new tool today, which is a graph. So hopefully you've been learning about these in math class. You have a basic idea about them. I have a few other videos about graphs, finding slopes and y-intercepts and what all that means. But I want to start you guys in the same place that my class will start. And so if you had me for a science class, you've either done an experiment or you've gotten data for an experiment or you've watched a video about an experiment where we took a car and we measured where it was over time. And so what I have here is 4 different sets of graphs that have data for us that we can look at, find the slope, and then use that to make predictions about where the car is. So here's our first set of sample data. If you look at the data that we have typed in here into this program called graphical analysis, you'll see that our time here goes by 1-second markings and we have position measurements. These position measurements are where the car was located at each of these times. So when I first started the stopwatch, at the very first moment of our experiment, our car was at 15 centimeters from that reference point. And you can see every 1 second I have a new measurement for where the car was. Now if you'll look at our line here, our data points, you'll notice that they're in the shape of a very straight line. And our line is straight and not curved or jagged or crooked because every second that passed in time, the car traveled the same distance as all the other seconds. So what this straight line shape of our graph means is that our car has a constant velocity. Or if you want to say it in a maybe lower level way, you can say that our car has a constant speed because, and this is really important, the slope of the line is consistent throughout the entire experiment. It doesn't get steeper, it doesn't get less steep. The slope stays the same. And what this means is that our car keeps the same speed each second. And now what we're going to do here is what we did before, is we're going to click on that bottom left hand corner. We're going to tell it to apply a curve fit. Now there's a lot of different things you could do here, but the button we care about right now is the linear curve fit because this looks like a line, not a curve. If we saw that it was curving up, we want to use a curve fit, but this looks like a very straight line. If I hit apply, it's going to give us a bunch of information about this line. Some of the stuff we care about, some of the stuff we don't. We don't care about the range. We know y equals mx plus b because we've learned it in our classes. So what we really care about are the m and the b. If you'll remember from the slope video, m is the slope, that's the rate of change. The b in the y equals mx plus b is the y-intercept, and that's the starting point. Now if you'll notice here, our b is 15, which means our line starts at 15, which means our experiment, our car, started at 15 centimeters. That's what the b means. And then m is the slope. Now what the slope is the rate of rising to running. And so what this says is every 1 second that goes by, my car moved 8 centimeters. And I'm going to add away from the observer. So my position went up because the space between me and the car got bigger each second. So the way I would communicate this graph in words is starting at 15 centimeters, the car moved 8 centimeters each second away from the observer. So in the second example, you'll notice just the first second you look at it, it looks very similar to our first example. And there are some similarities, but there's some big differences too. So if we look at our data, you'll see that at 0 seconds, Our starting point is 250, and then our numbers get bigger from there. If you look at our graph, our line goes up, just like last time. So just like last time, the fact that our line goes up means that we're getting further and further and further from our object every second. The object's measurement is getting bigger and bigger and bigger each second. Now, I did something tricky here, and I messed with the scale. So instead of going 0, 1, 2, I went 0, 5, 10, 15, and up from there. Notice the computer program did not care. It's totally cool using a different scale. Plotted our points beautifully, and as always, if we click the bottom left-hand corner, we tell it to add a curve fit, make sure it's linear because this is a line that we're looking at. It gives us a bunch of information, and once again, we don't care about anything except for these two numbers right here. The m is the slope, the b is the y-intercept. This is the rate of change. This is the starting point. So this number is a lot higher than our last number was because this car is moving faster. That's what the slope means in these equations. A high number for a slope means a fast car because that means it's covering a big amount of distance in each second. But just like in the last example, it's consistent. Every 1 second it runs, it rises 15 centimeters. Now, some of you who are looking closely might be looking at these numbers and saying, hey, wait a second, Mr. Stewart, these don't go up by 15s. That's because I'm going up by 5 seconds. So instead of waiting 1 second in between my measurements, I'm letting a whole 5 seconds go by, and then I'm taking another snapshot. So our last example was in the single digits. It was slower. This one's 15 centimeters per second, which is still pretty slow, but it's faster than our other one. It covers more ground in the same amount of time. So now when you look at this third example, you'll notice something very different from our first two. Our first two went up at an angle. This one goes down instead at an angle, which means that our position compared to our observer is decreasing over time. It's getting closer and closer and closer. If I had a measuring stick, my measurement would be going down each second. Now what this means is going to be different about our slope is that instead of having a positive growth each second, we're going to have a negative growth. So we look at our data, it's still going up by ones. Starting at 100, it's going down by what looks like 6s every time, but let me just run my numbers to make sure. So I'm going to click this bottom left-hand corner, apply curve fit, linear fit. It's a straight line. Again, most of this information we don't care about. What we do care about are these two things right here, the M and the B. The B is our starting point, which makes sense. It should be in the ballpark of 100 because our first data point from our data was at 100. And again, I made this data up, so I made it fit nice and pretty. So at 0 seconds, when we first started our stopwatch, we were exactly 1 meter, 100 centimeters away from our car. And then as time went on, every 1 second, I took a new measurement, and that measurement was 6 centimeters less than the second before it, which means the car is moving toward us instead of away from us. So if I was going to describe this graph and this data in words, I would say, starting at 100 centimeters, the car moved 6 centimeters toward the observer each second. I wouldn't say the car moved negative 6 centimeters, because negative 6 centimeters means closer to the observer. It's the exact same thing. In this last example, it looks like our previous example because our line's going down. So just like the last time, that means that our measurements are getting smaller over time. Our distance between us and the object is decreasing over time, which means it's going toward us. So if our line's going up, that means it's going away. If our line's going down, that means it's going toward us. The other thing we need to figure out from this data is what the slope is, because the slope gives us the speed of the object. A high slope, or a steep slope, a big number for our slope, means the car is moving fast. A small number for our slope means that the car is moving slow. So I go down to this corner again, apply the linear fit. It spits out a bunch of numbers at me. And again, the only thing I care about is right here, the M and the B. This is the starting point, so the car is starting at 1,500 centimeters, and it has a slope of negative 25, which means it's going toward the observer at 25 centimeters per second. So this is our fastest car yet. Our number is 25 centimeters, which means each second the car gets 25 centimeters closer to the observer, which is usually us, and it starts at 1,500 centimeters. So we've looked at the kind of data you would look at to make what's called a position versus time graph. And so I want to just kind of summarize from those 4 examples what we should have learned, what we should take away for this learning target, which is making and interpreting a position versus time graph. The first thing we learned is that we have straight lines, and the lines are straight because that means our velocity is constant. We will get to changing velocity, but we're not there yet. So right now we're just talking about if we keep a steady speed, we're going to end up with a straight line. And I'm only going to really give you 4 big examples here. One looks like this. That line is going down, which means it's going toward the observer. And it's not that steep, which means it's not that fast. Low slope, gentle slope going down. If I were going to put this in words, I would say this object is moving toward our observer at a slow rate. Another option I could use is this one. That is also going down, which means it's also going toward our observer, but our slope is steeper than our last example, which means it's faster. So if I was going to put this example, the purple example, in words, I would say this object is moving toward our observer at a high rate of speed, quickly, towards fast. There are 2 other options I can give you. One of them is this. That is a gentle incline, but it goes up. So I would say this is going away from the observer slowly. And then my last example that I could give you would be this one. That's also going up, which means it's also going away, but this one is much, much steeper. And since it has a steeper slope, we would say it's moving quickly away from the observer. So green is slow and towards, purple is fast and towards, dark blue is fast and away, and light blue is slow and towards. We're going to talk way more about how we use these, how we can use these to make predictions, and then ultimately we're going to distill all of this into a calculation and write it as an equation. This is Mr. Stewart. As always, keep learning no matter what.